Hello there. How do you do? My name is Professor Andrew Timming, and I am the author of this textbook, Applied Statistics, Business and Management Research. I want to start by extending a very warm welcome to you. I'm very pleased that you've dropped into this lecture series to learn how to be a budding data scientist. This lecture that you're currently listening to corresponds to Chapter 6 of the textbook. And in this lecture, we will focus on how to calculate and interpret an analysis of variance, also commonly referred to as an ANOVA. In Chapter 6, Lecture 1, I gave an introduction to an ANOVA, and I explained how it was something of an extension of a t-test, except that in the case of an ANOVA, we have 3 or more groups or categories that we're comparing means across. All right, let's do this. And here you can see the textbook that we're using in this lecture series. It's entitled Applied Statistics, Business and Management Research, published by Sage and written by yours truly. I hope you have enjoyed reading this textbook. I hope you will continue to enjoy reading this textbook. And I am very happy to receive any feedback that you might have for the next edition of it. Now, you will recall from the previous lecture where I gave an introduction to ANOVA that the key statistic at the heart of this methodology, of this statistical technique, is called the F statistic. When we learned about the t-test, the key statistic was the t statistic. In the case of ANOVA, the key statistic is called the F statistic. So when we calculate an ANOVA, the ultimate result of that ANOVA is going to be the F statistic. And the F statistic, which is a number, will say something about the magnitude or the size of the differences between the mean scores within our sample. So the larger the F statistic, the more likely that our mean differences within our sample generalize to the wider population. Corresponding to the F statistic is a p-value, and you'll recall that we use a conventional cutoff of 0.05 to suggest statistical significance. So any F statistic that yields a p-value that is less than 0.05, we can assume that the mean differences under consideration within our ANOVA are not simply an artifact of our sample, but in fact very likely generalized to the wider population. So there are 8 steps for calculating an F statistic. I've articulated these 8 steps here, and I acknowledge that the calculation of an F statistic appears somewhat intimidating for individuals who don't consider themselves mathematically inclined, let's say. But if you break up the calculation of the F statistic into separate parts, as I'll do here, you'll find that it's actually not as difficult as it appears at first glance. So let's look at an example using a small sample of just 12 individuals. This example builds on a scenario that we discussed in the previous lecture. And let's look at how we can calculate an F statistic by hand. Again, you wouldn't be expected to do any of this by hand if you were working with a big data set, because it would be extremely time consuming to do so. And with big data sets, that's why we use statistical software, statistical packages like SPSS and others to do the math for us, so to speak. But I think it's important when you're using SPSS and you click run, when you click OK and you do a statistical test, to have some sense of the mathematical processes in your mind when you do this. So let's go through an example. This is a hypothetical exercise. It's not a real exercise. This isn't real data. I'm only showing you this example for purposes of illustrating how to calculate an F statistic in the context of a one-way analysis of variance. This example goes back to the previous lecture where we talked about a potential relationship between an individual's musical preferences and IQ and intelligence. So let's look at the data that we have in front of us here on the slide. You can see that we have 12 employees. So our N equals 12, the total number of cases in our sample. You can see the first column is the participant. You don't actually do anything with that data. That just shows you that there are 12 individuals in this sample. And the next two columns is where we have our variables. So musical preference is our independent variable, and IQ score is our dependent variable. And if you look at our independent variable musical preference, you'll see that we have three categories or three groups. So those who have scored 0 have a preference for classical music. Those who have coded 1 have a preference for rock music. And those who have coded 2 have a preference for techno music. And what we're trying to ask ourselves with the statistical test is whether or not there's a relationship between musical preference and IQ score. In other words, is it possible that in one of those categories, perhaps classical, you might find higher IQs compared to the others, or lower IQs, or depending on how you look at it. Obviously, you'd have to put some theorizing into this. So let's have a look at the various steps we use to calculate an F statistic using these data. Step one, the first thing we do is we calculate this, what are called the sum of squares total. So I have the equation at the very top there. SST is the sum of squares total equals the sum of each x variable squared minus the total number of cases times the average squared. So you simply fill in the blanks. You can see in the next row down, we have SST equals, and then in parentheses, you'll see that I've taken each score, each of the 12 scores from the data set we're using, squared each one of them and added them up. And then I subtract, and then in parentheses, 12, because that's the number of cases is 12, times the average, which I've calculated for you is 114.5 squared. So if you go to the next line down, I've actually carried that a step further. So I've squared each number, haven't added them up yet. The next line down, we have the SST equals 158,862 minus 157,323. And this gives you a sum of squares total of 1539. So hold on to that number, 1539. Okay, the next step is to calculate what we call the sum of squares between. You can see the equation at the top there, SSB, sum of squares between, equals the sum of, so you have n sub k, this is the number of cases within each category. That would be 4, because there are 4 individuals that have a preference for classical, 4 have a preference for rock, and 4 have a preference for techno. So n sub k is 4 times, and then in parentheses, we have the average per each category. So you see x bar sub k, that refers to the average within each of those groups minus the overall average, which we calculated on the previous slide, which is 114.5 squared. So you can see this sort of broken down if you follow it step by step. In the second row, we have 4 times 121.5 minus 114.5 squared. So the 121.5 is the average IQ for the first group. That would be the individuals who have a preference for classical music. Then we have plus 4 times the average of the second group, which is 100.5 minus 114.5 squared. So the 100.5 is the average IQ for those who have a preference for rock music. And then you add that to 4 times 121.5. So that's the average IQ for those who like techno music, minus 114.5, which is the overall IQ squared. So you can see, just looking at this second line, the average IQ for those who have a preference for classical and techno music is identical. It's 121.5. But the average IQ for those who have a preference for rock music is lower. It's 100.5. But the question that we're looking at is that mean difference big enough to generalize? So if you follow through the next few lines down, you can see that we finally get a result of sum of squares between equals 1176. So hold on to that number in your mind too, 1176. Okay, the next thing we need to do is to calculate what is referred to as the sum of squares within. Now, there is a complex way of calculating this, but using simple algebra, we can derive this number based on our knowledge of the sum of squares total and the sum of squares between, which we just calculated. So the equation to calculate sum of squares within is sum of squares within equals sum of squares total minus sum of squares between. We already know sum of squares total is 1539. Sum of squares between is 1176. So when we subtract 1539 from 1176, we get sum of squares within equals 363. Okay, hold that in your mind. The next step is an easy one. So this is calculating the degrees of freedom within. That's DFW. And this is a very easy math problem. You simply take n minus k, where n is the total number of cases in your sample, and k is the total number of categories or groups in your sample. So in this case, our total n equals 12, and we have 3 groups. That would be those who have a preference for classical, for rock, and for techno. So to calculate degrees of freedom within, we simply take 12 minus 3, and that gives us a score of 9. Hold on to that one in your mind for a moment. The next step is to calculate what is referred to as the degrees of freedom between, not within, but between. We call this DFB. And this one is just as easy, if not easier, than the calculation of degrees of freedom within. So to calculate the degrees of freedom between, it's very simple. We just take the total number of categories in our ANOVA, that is to say the total number of groups, and we subtract 1 from that number. So you'll recall we have 3 groups in this particular ANOVA. In other words, we're comparing 3 different mean scores. The groups are, number 1, those who have a preference for classical music, number 2, those who have a preference for rock music, and number 3, those who have a preference for techno music. So 3 minus 1 gives you 2, so we know that our degrees of freedom between is 2. Just hold on to that in your mind for a moment as well, please. Okay, the next step to arrive at an F statistic is to calculate what we call the mean square within. That's the MSW, mean square within. So to do this, we simply take the sum of squares within, which we calculated above, and divide that by the degrees of freedom within, which we also calculated above. So the sum of squares within we calculated to be 363, and the degrees of freedom within we calculated to be 9. So if you simply take 363 and divide that by 9, you get a mean square within of 40.33. Now just hold that number in your mind. The next step is to calculate what is referred to as the mean square between. So this is a fairly simple calculation if you've already calculated the sum of squares between, which we have, and the degrees of freedom between, which we also have. So you'll recall the sum of squares between resulted in a number of 1176, and our degrees of freedom between corresponds to 2. So to calculate the mean square between, we simply take 1176 and divide that by 2. When you do that, you get a mean squares between of 588. Now just hold that number again in your mind, if you will. And okay, we've reached the final step in the calculation of an F statistic for a one-way analysis of variance. And again, this is a simple equation as long as you have calculated the mean squares between and the mean squares within, which we have. So you'll recall from the last couple slides, mean squares between corresponds to 588, and mean squares between corresponds to 40.33. So to calculate F, you simply take mean squares between divided by mean squares within. That means to calculate F, you take 588 and divide that by 40.33. This gives you an F statistic, in this particular case, of 14.58. So you can see there's a bit involved in the calculation of an F statistic. From beginning to end, it is a very complex math problem. But if you break it down into these 8 separate steps and you do one at a time, you'll see that that complexity kind of melts away a little bit and becomes somewhat easier to cope with. Now, obviously, we were able to do this by hand because we're dealing with a small sample. We only have 12 individuals in this sample that we're dealing with. Imagine if we had 2,000 or 3,000, how long it would take to calculate this out by hand. It would be impossible. Well, not impossible, but very, very difficult. So I want to congratulate you on having calculated the F statistic by hand, and let's think about now what an F equals 14.58 means. The truth is that in and of itself, an F statistic of 14.58 means very little. Without the corresponding p-value, you still won't know whether or not that F statistic suggests that the mean differences that we're looking at in this example are generalizable to the population. Now, when you use SPSS, you will not only get the F statistic as a result of your ANOVA, but the corresponding p-value that comes along with it. Now, the p-value in this particular example is p equals 0.002. So what does that mean? Recall that the cutoff that we use is that if p is less than 0.05, then we conclude that the result is statistically significant and therefore generalizable. And because 0.002 is less than 0.05, then we're going to conclude that there is some mean difference that is significant somewhere within our example. So somewhere between classical music, rock music, and techno, there is a significant difference in terms of IQ. Now, without further post hoc pairwise tests, we won't know exactly where that difference lies, right? We already know, if we think back to the slides that we went through, that there's no difference at all between classical music and techno. They had the exact same IQ. So presumably we can assume that the fact that the IQ for rock music was around 100.5, that's where you see the significant difference, right? So remember, the mean for classical and techno are both 121.5. So it seems to suggest this ANOVA test that we've carried out seems to suggest that the IQ of rock listeners is significantly lower than the other two. Thankfully, we don't have to calculate F statistics by hand. We can use SPSS to do it. And I've articulated a few steps that you can carry out in order to produce your own one-way ANOVA using SPSS. So the first thing you want to do is look at your descriptive statistics and frequency distributions for your independent and dependent variables. Then you want to define your group variable as what is referred to as a factor and your outcome variable as a dependent. You also want to request the homogeneity of variance test. This is the Levene's test that tells us whether or not the variances are roughly equal across our groups. The spread of the scores is roughly equal across our groups. You also want to request descriptive statistics, perhaps mean plots as well, and post hoc comparisons, which I would recommend should be Bonferroni corrected if equal variances are assumed based on your Levene's test. You can also request or calculate your own effect sizes to tell you something about the magnitude of the differences. And perhaps the most common one is Cohen's d, but there are other ones as well. So just like in the last chapter, we focused primarily on the independent samples t-test. And then at the end of that lecture series from the last chapter, from chapter 5, we talked a little bit about the paired sample t-test. We're going to do the same thing here. So this lecture series is focused primarily on the one-way ANOVA, which is a between subject test. It compares mean scores between groups. But there's also another method of ANOVA called the repeated measures, and this is similar to the paired sample t-test. A repeated measures, ANOVA, measures mean differences at multiple points in time, for example, at time 1 and time 2, right? It's a within group test rather than a between group test, and that means that it's comparing mean scores from the same sample but across multiple measures or points in time. And there are also ways, it gets quite complex, but there are ways you can add between subjects variables into more complex repeated measures ANOVAs, which are called mixed design ANOVAs. But just like with an independent samples t-test and just like with a one-way analysis of variance, the repeated measures ANOVA also gives you an F statistic, and it also gives you a p-value, and that p-value will speak to the generalizability of your results to the wider population. All right, so let's summarize what you've learned so far in chapter 6 of this book. We looked at the one-way analysis of variance, also referred to as the ANOVA, and we learned that this is a bivariate statistical test. So we have two variables, x and y. Our independent variable x has 3 or more groups or categories, and our dependent variable y is either ordinal or preferably scale and should be normally distributed. So what we do with an ANOVA is we compare mean scores of the dependent variable across the groups or categories of the independent variable, and then assess the magnitude of those differences to determine whether or not the differences are large enough to generalize to the wider population. In calculating an ANOVA, we calculate an F statistic and a corresponding p-value, and that p-value will tell us whether or not our mean differences generalize to the wider population. But the fact that we found a significant ANOVA doesn't tell us everything we need to know, because we need to also request post hoc pairwise comparisons so we can look at every possible configuration of pairwise comparisons within our ANOVA to see exactly where the mean differences exist and where they don't exist. And lastly, we learned a bit about the repeated measures ANOVA, which compares mean scores within groups, so within the same sample, but across different points in time. Okay, at this stage, I'd like you to pause this lecture and go through either by yourself or in groups the following 6 questions. Answering these questions will help you digest and better understand the material that we learned about in chapter 6. And okay, thank you very much once again for listening to me, for tuning in. I hope you learned a little bit about analysis of variance in this lecture series, and I look forward to catching up with you soon. Thanks. Bye-bye.